Hello everyone, welcome back to another session of a series of interviews conducted by the Department of Chemistry, University of Colombo. As the interviewers of this series, we intend to discover eminent scientists from a different angle. I'm Dhanushi Patirage, today Kitma Sajini and Dhirini Kaushalla will be also joining as interviewers. We all are fourth year undergraduates following honors degrees in chemistry and computational chemistry. I'm deeply honored to introduce Nobel Laureate Professor Martin Karplus to our interview today. Professor Karplus has contributed immensely to science. Among the contributions, the Karplus equation in nuclear magnetic resonance spectroscopy, molecular dynamics for biomolecules, and theories of protein folding take prominence.
He has co-authored two key reference books, Proteins, a theoretical perspective of dynamics, structure and thermodynamics, and Atoms and Molecules, an introduction for students of physical chemistry. Apart from the scientific publications, Professor Karplus has published his autobiography, Spinach on the Ceiling, a multifaceted life of a theoretical chemist. He was awarded the Irving Langmuir Prize in 1987 and the Linus Pauling Award in 2004. He was named the Theodore Williams Richards Professor of Chemistry at Harvard University, and now he is the Professor Emeritus at the same university. And also, he is the Director of the Biophysical Chemistry Laboratory, a joint laboratory between the French National Center for Scientific Research and the University of Strasbourg. Professor Karplus received the greatest appreciation in science for his work by being awarded the Nobel Prize in Chemistry in 2013 for the development of the multiscale models for complex chemical systems.
Good morning, Professor Karplus. We warmly welcome you to our interview and thank you very much for giving us your valuable time out of your busy schedule. Okay, Professor, in order to begin with the questions, let me ask you first question. Professor, you have come on a long way. So we would like to hear about a brief background about your childhood and how did it influence you to become who you are today?
Well, as you may know, if you read my autobiography, I was born in Vienna in 1930. And when Hitler was invited into Austria in 1938, my family had prepared us to leave Austria a few days before Hitler came in. And we went to Switzerland, and then finally we're able to come to the United States. And when we were there, and it turned out, as you may know, I had a brother who was 3 years older than I was. And he actually was given a chemistry set, and since he had one, I wanted one too, but my family felt having two chemistry students making explosives would be too explosive for the family, so they gave me a microscope, which at first I was disappointed in, but then I one day was looking through the microscope, which I still have, and which is in the closet here. I was looking at some runoff water in the street, and I noticed these little creatures, which I learned were rotifers, and they were swimming around, and they had little antennae, sort of like things which moved around and made them go in the direction that they wanted to toward food. And I was so excited about that. I showed it to my parents, of course, and some of my fellow students came over. And that was sort of the beginning of my interest in science.
It was really nice to hear about those, Professor. I think next, my fellow interviewer, Danu, she has a question for you.
Professor, we got to know that you published your first academic paper when you were 17 years old. So, would you mind sharing that experience with us? How did it happen? And what are the challenges you faced?
Yes, you're referring to a paper I published about birds. I was always interested in birds, took me to be able to identify them. And I, in particular, was interested in auks, which are small seabirds, which you can see sometimes when there are big storms and they come close to the shore. And so I wrote a short paper and had to decide where one might publish it. And there was a journal of the Audubon Society, and they thought the paper was interesting enough to publish. There was one very early paper. The other one actually, which was a little bit later, was when I was an undergraduate at Harvard and was invited to go to Alaska. And there I spent a certain amount of time I was the junior investigator with some of my senior colleagues. We were staying in a hut in Umiat, away from the main organization place, which was there to study various aspects of how humans adapt to the Arctic. What I did was organize my senior colleagues to study robins, which are birds which occur in Alaska and also in Massachusetts. And what we discovered was that the robins in Alaska, where there was essentially continuous daylight, feed their young for about 23 out of 24 hours a day. And it appeared that because they were being fed so much more, they grew more quickly and left the nest earlier. And since the nest, which was on the tundra, was very much exposed to various animals that ate the young, safer. And so I published a paper saying that although the trip from Massachusetts and other states to the Arctic was dangerous, the danger were made up for by the fact that they were less exposed to danger when they were nestlings. And this paper was published in Ecology, and I discovered recently that people are still arguing about it, whether because I hadn't made a study of 20 robins, whether my results were really meaningful or not. And I enjoy reading that even though this happened, now 75 years ago, more or less, people are still interested in it.
Thank you, Professor. I think that would be a great inspiration for our young viewers. So over to you, Kitma.
Thank you, Dhanushi. Professor, you have contributed to many fields in physical chemistry, including chemical dynamics, quantum chemistry, and most notably molecular dynamic simulation of biological macromolecules. So what was the inspiration that helped you to become proficient in all these streams in chemistry?
Well, I'm not sure I can answer your question completely, but what I tried to do in my life was to move every 5 years from one institution to another, starting at the University of Illinois. Then I went to the Columbia University 5 years later. Then I came to Harvard, and then I actually went to Europe. And by moving in this way, I had new colleagues and interacted with them, and was inspired by my interactions to work in these various different fields. And one thing that I found was very good was that starting a new field actually made it very exciting for me because I didn't know anything about it. And in fact, I think that that was good because I didn't sort of have to follow what other people had done, but had to find my own way. And with these different inspirations at the University of Illinois, there was a strong group of people in nuclear magnetic resonance, and in discussions with them, I realized that people were making measurements but didn't quite understand what they meant. And so I developed an equation, which is now called the Karplus equation, which is widely used by organic chemists and now by biochemists. And probably I'm better known to people to students who take any course in organic chemistry, not for the molecular dynamics, which we've done more recently, and which was involved in the Nobel Prize, but for this equation. And then when I went to Columbia, I had interactions with people who were interested in chemical reactions and had also access to what was then a supercomputer at the Watson Laboratory, and using it permitted me to study chemical reactions. And we studied the simplest chemical reactions, which is the reaction between a hydrogen atom and a hydrogen molecule. So, as you may know, for two-particle systems, you can solve the reaction essentially analytically, but as soon as you have three particles, you have to simulate it. And having this supercomputer available made it possible for me to study this. And it was a time when Dudley Hirschbach, who was at Harvard, was doing molecular beam experiments, which actually studied simple collision, triatomic molecule collisions. And so I was inspired to look at that. And then when I returned to Harvard, I had decided that I wanted to study biochemistry, which had been, as I mentioned, the rotifers earlier, an interest of mine for a long, long time. There again, I found colleagues, both in the chemistry department and in biochemistry, with whom I could interact to learn how to study some of these biochemical reactions. Now, does that answer your question?
Yes, Professor. Thank you very much for that explanation. Over to you, Dilini.
Yes, Professor. Actually, I think my next question was answers already, because I was going to ask about the exchange reaction between hydrogen atom and hydrogen molecule. So, Professor, is there anything would you like to add to that other than what you have already said?
Well, I guess I didn't mention, and that's something I should have mentioned, is that, of course, in order to study any chemical reaction, even this very simple one, you need to be able to determine the forces of interaction on each of the atoms. And to be able to calculate the forces, you need a potential energy surface, which gives you the energy as a function of position. And what I did with Dick Porter, whom I had met when I was at the University of Illinois and invited to come with me to Harvard as a postdoctoral fellow, was to develop this potential energy surface, which is called the Porter-Karplus surface now. It partly was based on empirical information, and it was a very accurate surface. And having this surface, we could take the derivatives as a function of position, which would give us the forces of the atoms. And from that, starting with certain initial conditions, say a hydrogen atom far away from a hydrogen molecule, and then observe what happens as the atom approached. and doing this over and over again. In some cases, the atom approached and went out again and no reaction took place. And in other cases, the atom approached, picked off the atom nearest it, and the other atom went off. And that was essentially the chemical reaction. And so we could determine what fraction of the collisions led to reaction and what fraction of the collisions did not. That gave us a more complete understanding of this particular reaction.
Yes, Professor, thank you for your detailed explanation. Over to you, Dhanushi.
Thank you, Dilini. Professor, the first application for the classical mechanical potential function was the simulation of bovine pancreatic trypsin inhibitor, which is also known as BPTI simulation. So, Professor, we would like to hear how this research idea came up and a brief explanation about this BPTI simulation.
Basically, after having worked for a while on the simple chemical reactions that I was just talking about, I felt I understood these reactions. We had studied many other ones with colleagues, and I had the idea that maybe one could use the same methods we had used for the simple molecules to study macromolecules. And I talked with my colleagues about the possibility of trying to do something like that, which would be essentially the same thing as we did for the H plus H2 reaction, that we would get an empirical potential energy surface. And from this potential energy surface, we could find the forces on the atoms and then integrate from certain initial conditions the motion of the atoms in BPTI as the molecule, which was the first molecule we studied. Now, why did we study BPTI? Well, it was really for two reasons. One, that it was relatively small, having only around 500 heavy atoms. And secondly, that a very accurate structure for it had been determined at this time by the Huber group, who also received the Nobel Prize for his work in this general area. And so I asked my colleagues in chemistry at Harvard what they thought of this idea. And they said, well, you know, we have to work very hard, as I mentioned earlier, to study very simple chemical reactions. You must be out of your mind to think that you can study such a complex system. And my biological colleagues said, well, if you could do it, it wouldn't be of any interest to us. Well, in spite of that, I went ahead and did do the simulation with some of my postdoctoral fellows, Andy McCammon and Bruce Gillen. And it was, of course, the beginning of simulations of biomolecules, where now people are doing, I mean, thousands of people are actually doing this. And so this is a lesson to be learned, that if you have a good idea, or what you think is a good idea, and people discourage you, saying you can't do it, it's not meaningful, you should stick with this idea and go ahead and try to work it out. Though you have to realize that sometimes, of course, you may be wrong, and then you will have wasted a little bit of time. But if you really want to do something good, you have to have ideas, stick with them. And one other thing I should point out is that to get ahead with this, you really have to work very, very hard. It's not enough to have the idea, but it's hard work, as I discovered in my life, to actually be able to work out this idea in a useful manner. So that's, I hope, a lesson that all of you will take away from this conversation today.
Thank you so much, Professor, for that advice, and thank you for the great explanation. Over to you, Kitma.
Professor, my next question is about CharmGUI. CharmGUI has been used by many researchers, and it is a well-recognized tool in molecular modeling and simulation communities. And also, it provides an effective one-stop online resource for the biomedical research community to conduct innovative and novel molecular modeling and simulation research. Actually, I'm very excited to know how you built this platform, because I'm also currently using CharmGUI in my undergraduate research. So what were the issues you had to overcome while you were building this platform?
Well, I should say that actually it wasn't I who built CharmGUI, but it was somebody else. And so you would have to ask him.
I'm sorry, Professor. So we will move on to the next question. Over to you, Divini.
Yes, Professor. Yes, my next question is about protein folding. We know that protein folding was one of your main focuses. So, Professor, we would like to know about the progress from the beginning of this area of research and how you got to study the protein folding.
Well, as I already mentioned, we had studied the molecular dynamics of the motions of a folded protein molecule. And so the next step was to try to understand how a molecule, the folded molecule, could be formed. The amino acids were put together in a certain sequence on the ribosome, and after it came off the ribosome, so that's another whole story, it folded up to the right structure, though sometimes misfolding occurred. And so we began to wonder how folding could occur in nature. And the first attempt to approach this problem was with David Weaver, who was a professor at Tufts, but came over to work with me. And there we took a very simplified model to represent the protein and studied how it could fold up. And this was very early, and the data weren't available to test what we had proposed. That was actually relatively recently, well, now it's probably about 30 years ago. Time has passed. And from this very simple model, then we went on to try to study the folding of a protein. Now, one thing you have to remember is that an important aspect of protein folding, or being able to fold, is the fact that many of the atoms of which amino acids are composed are hydrophobic. They want to get together with each other and get away from water. And that's one of the forces that causes the protein to fold. And we again started with very simple models. There are some very small proteins that have been studied experimentally, and where it was possible now with real supercomputers, and not the ones that I had available when I worked at the Watson lab, to do simulations of small proteins for milliseconds or so. And actually, that's been done on supercomputers designed by the Shaw group. And there one can actually follow the full folding reaction. But that is something that they did and not I did. So to really study the folding of a protein was beyond, in detail, was beyond what I was able to do at the time when I began to look at it.
Thank you, Professor. It was really interesting to hear about how science actually meant to you. Kitma, you have a question now, I think.
Okay, Professor. My next question is, when doing research, it is hard to discover everything on the first attempt, and there will be failed attempts too. So, what advice would you like to give to the students who have less experience in research about how to face those challenges and become successful without giving up?
Well, in a way, I think I already answered the question a little bit earlier as an aside about the fact that you should really have faith in yourself and not give up, even if people tell you your ideas are not any good. Yeah. So,
thank you, Professor. Over to you, Kitma.
Thank you, Dhanushi. Professor, you have recently published your own experiences in a book, Spinach on the Ceiling, A Multifaceted Life of a Theoretical Chemist. That book would guide many future scientists like us. So could you please tell us what inspired you to write this book and how did it feel when you published your own life story?
Well, my main reasons for publishing this book, there are several reasons actually. One, I felt that the experiences that I had had in going from a young student to getting a Nobel Prize would be something that could help to inspire young people. I also wanted to remind myself and my family of what I went through in going this far and what was important in doing so. And so I hope, that young people like you, and I should say I'm very impressed by the questions you're asking. You really did your homework. And that, you can see what one has to go through to be able to get far in whatever field of interest you may have. And I hope the book will do this.
That is really interesting to hear about your autobiography, Professor. And I think thank you very much for that explanation. And I think now Dhanushi has another interesting question. Dhanushi?
Yes, Kitma. Professor, as we mentioned earlier, you received the Nobel Prize for the development of multiscale models for complex chemical systems. So, Professor, what was the impact of your work had in the field that resulted in this great achievement?
Well, this is a rather complicated story. I personally think, and I have said this, that I really received the Nobel Prize not for what it was officially given, for methods of studying complex systems which play a small part in what is important about my work. My feeling is that really if I hadn't studied the molecular dynamics of macromolecules, protein folding, as has been mentioned, and other things, we would never have been given the Nobel Prize. And the choice that was made in giving it to us, talking about chemical systems, was that the Nobel Committee wanted to find a way of giving the prize to 3 people, more and more, because there are many people who would deserve the Nobel Prize, rather than giving it to just one person, as they did in the early years. They want to find a way to give it to 3 people. And it was this complex systems, which Michael Levitt, Ari Warshall, and I studied, that gave them away to give it to 3 people at the same time.
Okay, Professor, let's move on to the last question. Dilmi? Hitma?
Professor, I have one more question regarding your life story. I got to know that you have a range of hobbies, including photography and cooking. And also, you have organized your own photographic exhibition. So, what was your secret behind managing your time to engage in all these activities?
People say that scientists have a secret garden. My secret garden consisted of photography and cooking. And when people ask me about this, well, the photography just began by accident in some sense, that when I was getting my PhD, essentially at Caltech, working with Linus Pauling, who won the Nobel Prize in chemistry and for peace. My parents gave me a Leica camera, a very good camera, outstanding. And so when I went to Europe, to Oxford as a postdoctoral fellow, I traveled around a lot, taking the terms, which were relatively short, literally being in Oxford for the terms, and then between terms, which was 8 weeks or so, traveling around in Europe, taking pictures. And I went, as you know, all over the place. And continued to do this by accepting invitations to speak in areas where I wanted to take photographs. And I never knew that these photographs I took were anything special. But one time when I was in England as a special researcher, my wife showed some of these pictures to a photographer and practiced mainly developing the pictures and framing them. And he said, well, these are wonderful pictures. You really should show them. And so my first exhibition was actually when I was in Oxford. And then one time I was, somewhat later, I was collaborating with someone who I knew was on a committee of the National Library in France, the Bibliothèque Nationale. And I mentioned to him when we were sort of through talking about the science, Jean-Pierre Changeux was his name. I mentioned that I had some photographs, and I showed them to him, and he in turn arranged for me to show them to the curator of photography at the Bibliothèque Nationale in Paris. And she in turn thought they were really great, but I may have been known as an outstanding scientist, but I was not at all known as a photographer. And so she worked very hard to get the head of the Bibliothèque Nationale to be willing to show my pictures. She had fallen in love with them, and we had gone back and forth. And so she arranged for an exhibition which occurred just before I received my Nobel Prize. So I'm really proud of the fact that I wasn't given this exhibition because I had a Nobel Prize. And the curator, whose name was Sylvie Aubenas, was responsible in a way for my having exhibitions as a photographer. But it certainly is true also that after I got the Nobel Prize, I probably got more invitations to show my photographs, and it was really all over the world. The latest exhibition was in Venice a year or two ago, and also at the institute where I worked when I was in France, there is a permanent exhibition of a selection of my photographs. So that's the history of my photographic development and my secret garden in that area. As far as cooking is concerned, I've always loved good food, and actually began cooking when I was very young, and when my mother, who had been a dietitian at my maternal grandfather's clinic, was cooking, and I would sort of hang around the kitchen and see what she was doing. And she made simple things, but they were made with very good ingredients. And sometimes she let me help or cook something. And then went on when I was a graduate student at Caltech, where after the first year, I roomed with some other graduate students that I had met through the Science Talent Search. And there I did the cooking, and they did the washing up and everything. And so I developed further my interests in cooking. And then the next step was when we had bought a chalet in France above the city of Annecy. And there was a famous 3-star restaurant, and we would go there at least once every summer to celebrate. We weren't, wealthy enough to go there very often, but sometimes, I would thank the Maître d', and one time I asked him, could I go and meet the chef? And so, I was invited to do that. And I asked him whether I could come down from our chalet to the restaurant and hang around in the kitchen. And he was very nice and said, sure, I could do that. And so I did that for several summers. And certainly I didn't really do anything to help things, but I did learn began to learn what was going on. And then later, another event happened where we were planning to go back to the United States from the chalet, and it turned out that there was a strike, airline strike. So after we had closed up the chalet, and I was driving back to Paris, I had some extra time, and so I went to Rouen, where there was another 3-star restaurant. And there I had begun to learn things, as I said. And there I actually started to help out in the kitchen. And so this went on, that I would, we would go to 3-star restaurants. I would say what I had done before and ask whether I could help out. And slowly I actually became educated enough in what one does in high-class cooking that I could really help. And finally, what would happen is that I began to replace the person who had, his day off or something. And that's the story. And so I cooked in many famous restaurants in France, and then also in Spain. But now that's finished. Now the cooking I do is just at home. And as I have said, the only real chemistry I do is cooking. All the other is just theoretical. And yeah, my family is very happy to have me do the cooking and are willing to do the washing up and other things. And sometimes my son helps me in the preparation. And it's really a nice family event.
Professor, that is really great to hear. Personally, I feel like I'm more inspired to follow my hobby as well. With that, I think we have come to the end of our interview, Professor. Thank you for your advice, for your inspiration, for giving us creative energy to grow and do something new every day. We are truly grateful to have had this interview with you today. And thank you very much again, Professor Karplus, for giving your valuable time, sharing your knowledge, amazing experiences, and guidance you have given us. May health and happiness be with you always, Professor.
Well, thank you. And let me just say that I very much enjoyed this interview, and I'm very impressed, as I mentioned already before, how much you have done to do your homework to make this interview really worthwhile, hopefully for you, and fun for me. So thank you very much. And thank you for your professor for arranging it. So.
Thanks again, Professor.
Thank you, everyone. So stay tuned with us for more remarkable interviews with eminent scientists. Have a nice day.
Bye.
Goodbye, Professor.
Bye, Professor. Thank you.